Okay. Okay, we will start the meeting in 1 minute. Okay, shall we start? So this is multi-pass working group meeting. Please make sure you are in the right room. And then my name is Yoshi Nishida. And unfortunately, Phil could not make it to this working group meeting. I think he will gonna join this meeting from remote. Okay. Something. Work? Something is strange. Okay. Like this? Okay. Okay. And note taker, thanks for Christoph for volunteering note taker. And thanks for Miria taking care of Java. And just a reminder, when you speak up at the mic, please say your name before you start making comments, so that note taker can write down your name in the minute. And also, when you submit your internet draft, please make sure put Mptcp in your title of your draft, so that chairs can track the status of your draft. And also, in this meeting, please make sure write down your name on the blue sheet. Okay, so this is your user note well. I think you already get familiar with this one. So this is a reminder of IETF policy with regard to your behavior, your policy, your privacy, your intellectual property, your copyright, and so on. So if you have any concern about it, please take care of it. Please take a look at it carefully. And you can find same contents on the IETF webpage. Okay, so this is today's agenda. So first, Chair will talk about working group status updates. And after that, we are talking about implementation updates. And Christoph will talk about iOS and Linux updates. And then if you have any other updates for implementations, you will have a chance to speak up. And after that, we will move on to the individual presentation. At first, Geo and Marcus will talk about multi-pass TCP extension for robust session establishment. And after that, Nicholas will talk about some experiments of Mptcp over satellite networks. And after that, Heoi and Chi will talk about multi-pass TCP extension for trust and prediction. So this is today's agenda. Any comments, suggestions to the agenda? Okay. Now let's move on to the working group status. And it took for so long time, but finally we finished 6824 bits draft. So it's in RFC editor queue. So it will be published very soon. And I really appreciate your support for this draft. And thank you so much. And also, we have mentioned this several times already, that we don't have active working group item right now. And this is just a reminder. So this is a list of the milestones of our working group. And then we have done many stuff. And then in our past meeting, we discussed about publishing enhanced API draft. But our consensus was that we don't have enough energy to publish this draft. So we skipped this one. And then rest of the item was Mptcp standard track protocol. And this is just finished right now. And as a result, we don't have a working group item anymore. And then, as you know, we mentioned several times already, we cannot run working group meeting without having a working group items. And then, so right now, Chair and AD are continuing discussing about this one. If we cannot have enough, working group items very soon, we need to think about closing working group. I know we still have some energy in this community because every time we have meeting, we have some interesting presentation. Just like today. Today we have 3 interesting presentation. But in order to keep the working group, we have to have some working item that creates standard. That's what we need to, if we want to maintain the working group, that's what we need. And then we do not make any decision in this meeting, but we still, discussing. And then I think, we might make some decision before Vancouver meeting. That means we might close the working group before the Vancouver meeting if we don't have enough energy. So if you have some items to work on, you should, I encourage you to, make it hurry, submit a draft, and then announce a mailing list and encourage people to read the draft and then support the draft. And then that way, I think we can think about, we still have some energy to keep the working group. But just in case, even if we close the working group, this does not mean IETF do not work on Mptcp. In this case, most likely, TCPM will be the venue for the Mptcp topics. Christoph, you want to say something? Oh, okay, I see. Okay, so most likely, but it has not been decided yet, but most likely TCPM will be the venue for the Mptcp topic. That's the case. If we close the meeting, close the working group. And so that's the status of this working group. Any comment, question, suggestion, or addition? It's okay. Miria, you want to say something?
Just very quickly on this point. So I think the TCPM charter already includes minor extensions to TCP. So it includes also Mptcp because it's part of TCP. But I think it would be good discussion with the chairs there to potentially update the charter and make this explicit so people know where to go.
But still, we haven't decided it. Yeah. Yep. Okay. Any questions? Okay. Move on to the next topic, implementation updates. So, Christoph. Yeah, fine.
So, in terms of implementation updates, we released iOS 13 in September, and if you have seen the WWDC presentation in June, we are now using Mptcp for Apple Music to stream the music to the devices, and we see a great reduction in audio stalls thanks to this. We are also now using it for Apple Maps when people are searching and for getting directions, and it allows us to handle the Wi-Fi to cell transitions. So that means, at least inside Apple, we have Siri, Music, and Maps to our first-party users of Mptcp. Besides that, in the Linux kernel, there's now a community working on upstreaming Mptcp to the official Linux kernel. This community is being driven by Red Hat, Intel, and Tesseres. and we are making great progress. And we hope that in the coming months we have the first part of Mptcp in the upstream Linux kernel.
Okay, I have a clarification question. So in my understandings, Apple's Mptcp implementation is 6824 version, and then Linux version is 6024 bits version. Am I correct?
Yes, that's right. The multipath TCP upstreaming is aiming for 6824 bits. Our implementation currently is the old standard. One point here is as Red Hat, Intel, and TSRS are implementing Mptcp from scratch here in the Linux kernel now, and because they are not used to coming to the IETF, they are actually reading the IETF RC as it is, and sometimes are finding some issues that are a little bit confusing, and so they have actually some feedback to provide to the BIS draft. I know it's late, but it's just now that they are reading the draft. Yeah, it's more like clarifications, not like no big deals. Yeah.
Okay, but it might be possibility to be a draft.
It's mostly about wording and making sure that things are spelled out in the way they should be, so that it's unmistakably clear.
Okay.
Yeah, I mean, that's kind of the purpose of the editing step we have at the very end. So I think we should address this comment and take them in and just like maybe send an email to the mailing list to make sure everybody's aware. But if it's really purely editorial, I think it can still be addressed.
Okay. And then probably this is a difficult question for you, but if you have any plan that Apple will support this draft, if you don't want to talk about it,
long term, we are probably going to do it. I don't have a timeline for that. We will have to see. One thing is that the 3GPP ATSS standardization of the Mptcp proxy uses the BIS version of the draft. So ultimately, if we will want to support that, if we will want, then we will have to implement the BIS version.
Okay.
And I think more implementations will have to as well.
Okay. Thank you. And if you have any other implementation updates, this is a time for you to speak up. Anything? Okay, so now let's move on to the individual presentation. And I think Marcus? No. Okay, you can discuss.
Markus Armen from Deutsche Telekom. So I want to give an update to our draft about robust session establishment for multipath TCP. It's now the first time that we have an additional contributor. It's Jiao from Huawei. She's also here today. So in case if there are later any questions, she can answer as well. First, I want to give an overview about the updates since last time. We did a merger with the initial path election draft. It was mainly written by Jiao, and now we merged it into the robust establishment because it had more or less the same goals. We renamed the original Roby extended solution from the first draft version now to Roby eSIM, enhanced SIM. What it means we will see in the next slides. We're adding two new solutions, Roby IPS for initial path selection and Roby Timer. The initial path selection solution is coming from the merger with the initial from the merger with the initial path selection draft. We have now an improved document structure, which means the different solutions for robust establishment. We distinguish between solutions which require multipath TCP protocol adaptation or does not require. And also we started to define fallback concepts. I will explain this further in the slides. Just as a short recap, what is robust session establishment about? The standard multipath TCP in RFC 6824 and even the BIS are pretty much relying on a functional path for the initial session establishment. If the path selected for the initial multipath TCP session establishment does not work, no communication can happen, even if there are other working path or links available. And with robust establishment, with the robust establishment draft, we directly address this and try to elaborate different solutions to deal with this issue. The draft now in the current state includes 4 solutions. That is the Robi timer, Robi sim, Robi eSIM, and Robi IPS. But it also contains description about combination of those solutions. Again, that we will see during the presentation today. Starting with the Robi timer solution, that is a fairly easy proposal. So that makes use of the TCP retransmission timer. So it starts with the standard RFC 6824 session establishment. Here, for example, in this figure on A1, from A1 to B1. And if this expires, then it starts to use the next path to make this session establishment happening. So we see no conflict with the existing multipath TCP standard, and at least it would guarantee a session establishment in case there is a functional path. However, it brings in some delay. So if the first path fails, which we selected, then it needs at least the time to get the retransmission timer expired until the next path can be used. And if you have several paths failing, then it sums up. Then we have the Robi sim that was already part of the first version of the draft. That makes use of simultaneous establishment, so using any path available for the session setup, so that we can see in the figure here as well. So we start a SYN request on A1 and A2 simultaneously, and the request which is acknowledged first will be then selected at the initial path, and the other one or ones are resetted afterward with the TCP RST. What you can see at step SA61. So that is also in line with the standard, and it only relies on the functions which are provided from the standard itself. That is now new in the draft. That is the initial path selection logic. So that try to make use of a heuristic and tries to learn over time which path could be the best. Maybe that is also something which is included in the iOS with the Wi-Fi Assist. I'm not sure if this is similar, but yeah, as I said, it tries to learn over time which path has the highest probability to succeed. And here we have two examples how it could work. If I start on the right figure, the figure 6, it will, whenever an application requests a multipath TCP session, it will try to make a decision which path could be the initial, the route for the initial connection setup. If it is the first connection, though no heuristic available, then it could use the default route of the operation system. Otherwise, it will use the information it has available and select the route for the initial path establishment. On the left side, it's a little bit simpler, though there's no decision if a heuristic is available or not. So it will always use the initial path selection logic to select the proper path. But that also means maybe it fails when not enough information are available. The Roby eSIM solution, that was the former Roby X or for extended in the first version of the draft, and that enhance the SIM solution. As I explained, for SIM we simultaneously use, or we make simultaneously use of all paths which are available to establish a multipath TCP session that will guarantee that a multipath TCP session becomes established as long as there is one path functional in the system toward the destination. With the SIM solution, so without the E, this means we have a lot of overhead because we reset all paths but one. With the Roby eSIM, we make use of all the simultaneous establishment, and with the MP joint cap option we propose in the draft, though that is in step SA6.2 in the left figure on the bottom, we can make sure that any path which is not selected after the whole process to being the initial path can be directly merged. So it's not required anymore to have the traditional MP join process. We can make a direct use out of it. That has several benefits, which we also explain in the draft, also related to the BIS document, where you compare to the old RFC 6824. You need now a reliable ACK in the three-way handshake, and with Roby eSIM, you can relax this a little bit. So please have a look for details into the draft, or we can discuss this afterwards. On the left figure, we have an implicit connection setup, which means we don't have a negotiation between client and server about the Roby eSIM functionality. Whereas on the right side, we have an explicit negotiation using the Roby eSIM EN multipath TCP option we also propose in the draft. Okay, that is, sorry, what I forget to mention is for the Roby eSIM, it needs Mptcp protocol adaptation.
You mean you need to assign new option?
Yes, at least the MP join cap, yes. It's the same now for the Roby IPS, including the server RTT functionality. We could make use of the RTT information available by congestion control to make a more sophisticated decision about which path could guarantee an initial path establishment. And that is exactly what we are doing here. But there is the case, imagine that the IPS is working in a mobile phone and you have only downstream traffic, so you transfer traffic from the internet to the mobile phone. Then you have this information only available on sender side. So not in the mobile phone itself, it's on the remote host. And for that, we propose the LRTTEN option to be defined, which can carry the RTT information from the remote host to the mobile phone, for example, so that it can be used in the IPS logic. That is now one of the combinations I mentioned in the beginning. So that is Roby SIM and Roby IPS combined. So in case the IPS has not enough information for selecting a proper path in the beginning, so there's not enough heuristic, then it can use the Roby SIM in the beginning, and afterwards then if enough information is available in the system or in the IPS logic, then it can fall back to pure IPS. That is a combination of Roby timer and Roby IPS. So the same, if not enough heuristic is available, it can use in the beginning the timer solution, and when enough information is available in the system, then it can fall back to pure IPS. Yes, so that are the three options we propose currently in the draft. So that is the in the middle, the MP joint cap, what we need for the eSIM solution. It's on the top, the eSIM EN option to make an explicit negotiation for the eSIM solution. We are not sure if this is required, but if explicit negotiation is wished, then we need it. And on the bottom, we have the RTT EN. So in case we want to have RTT information from the remote host for some heuristic functionality. That is a table which is also part of the draft itself. It gives you a quick overview. What are the features of the individual solutions? I'm not sure if we have time to go through. Do we, or?
How much time you need?
3 minutes.
Okay.
Okay. So give it a try. So on the left side, we have different scenarios listed, and then over the columns we compare the different solutions with the standard multipath TCP. So in case we have packet loss on the initial path, though part of the handshake cannot be transmitted, then for multipath TCP, this at least means we have a delayed connection. For the Roby timer, this depends then on how long it requires to trigger a next try on a different path. For the Roby SIM, it has no impact because we simultaneously try to establish a connection on any path. So at least if there is one path available without packet loss in the system, it has no impact. For Roby eSIM, it's absolutely the same. And for IPS, it means a delayed connection if the selected path by IPS is affected by packet loss. If the initial path is broken, so that is a second row, then for multipath TCP, that means there is no connection possible. For timer, it is then depending on how long it needs to get the timer expired and to get a trigger to try it on another path again. For the Roby SIM, it has no impact. For the eSIM as well, and for IPS, it's the same. There is no connection possible. Now in the third row, we consider what it means in terms of how long it requires to establish an initial path. So for multipath TCP, it's depending on the default route characteristics. For the Roby timer, it depends on the default route plus possible tries on other paths. For Roby SIM, it's depending on the fastest path in the system. For Roby eSIM, the same, and for IPS, depending on the selected path, which could be the default route, but could also be something else. In the fourth row, then we have the same consideration, but for multipath session setup. So that means at least it needs a second path in the system to provide multi-connectivity or multipath usage. So for multipath TCP, that is depending on the multipath capable handshake for the initial path establishment, plus the MP join process for a subsequent path. For Roby timer, it depends on how many initial path establishment it requires, plus the following MP join process. For Roby sim, it's only depending on the handshake of the fastest path in the system plus a later MP join. For Roby eSIM, it's a little bit different. There we can reach the highest gain because we can there make use of all the path or all the handshakes we simultaneously started. So we don't have an MP join anymore, and we have the fastest multipath session set up over all the solutions in the Roby eSIM. And for IPS, it's also the standard MP-capable process plus MP join. And the most important thing now in the last row, which of this solution guarantees at least session setup. So for multipath TCP, it's depending on the default route. Roby timer, SIM, and eSIM can guarantee session setup. And for IPS, it depends on the selection. So next steps. Is this draft ready for adoption? And second, are there any comments from your side?
Any comment, questions? Okay, I think, this version is 25 pages for the draft. So it's, compared to the previous version, it gets very matured, I think.
Yes.
Yeah. And then I think this is useful idea because, you can establish MPTCP session very quickly without wasting any resources.
Yeah.
And so my question is, if someone want to support this one, and then especially if you want to implement this one, that would be great. So anybody have some interest in reading draft, reviewing draft, or implement draft? Could you speak up a little bit?
In any case, we could also consider to make this part of the next hackathon.
No, okay.
Could also be an option.
Yeah, right. And in your company, there is any plan for implementing this one?
Unfortunately, currently we don't have any resources for that. So that's why it would be good to have additional contributors.
Okay, just redraft, and if you have a comments, please send on the mailing list.
What are the prerequisites for a working group adoption? Yes.
Okay, I want to see feedback. So right now, people don't say support or not support.
Yeah.
So
maybe
we can encourage people make some opinion on the mailing list.
Yeah. Okay.
Yeah.
Thank you.
Yeah, thanks for the nice draft. It's getting matured.
There's one more question from Phil from the Jabber. Are there any experiments of how often this idea gets you any significant gain?
So if you check my presentation from the IETF 104, there we have some experiments presented, and there's also a paper out where we did several tests on what can be gained, and there are huge gains you can reach. Maybe they're the only question how often it happens, or you need it in reality. Sure.
Yeah, I think that's Phil's question. Yeah.
Yeah. But there we don't have any data about that. But it's pretty likely that, for example, with a mobile phone, it happens that you are connected to Wi-Fi hotspots, which are not capable to guarantee a session setup or maybe delay the session setup at least.
Thank you so much. Nicholas? Okay. Go ahead.
Okay. Hello, everyone. During last IETF, and more specifically during the social event, I had a chat with Phil on the problem we had on some Mptcp deployments and performance. So he thought it was interesting. So here are our issues, what we try to do, some evaluation of performance, and we don't understand everything we measure. Just to warn you that there are some strange things happening, and well, let's go through it. First, my presentation is in two parts. First one is Mptcp on geosatellite access, and the other one is on lower Earth orbit satellites. So for those who are not familiar with geosatellites, they are mostly at 36,000 kilometers, and so we have 600 milliseconds RTT. And because of that, we usually deploy TCP proxies. So what TCP proxies do, that is an example of what they can do. They basically intercept the scene, send the CAC to the host. So we have a quick establishment of the connection between the host and the first proxy. Then we have a specific protocol between the two proxies, and then a third part of TCP connection. So when we go in how Mptcp and shakes and connection establishments work, this is an example we follow throughout the presentation. We have host A with 2 addresses and host B. So we have the connection that is been done on whatever LTE or fixed network. And we have the exchange of MP capable data between host A and host B. But the main problem is if we try to open a subflow on the satellite link, if we just take our open source proxy or even a commercial proxy, if you don't adapt it, basically when you receive a scene plus an MP join, it just forward the scene. That's what we measured. So the problem is because it sends a scene ACK to the second address, the Mptcp connection cannot happen. So we have done some modifications to our open source proxy to be able to establish Mptcp connections. So what we do is instead of sending, so I hope it's clear, but when the proxy receive the thin and the MP join, instead of just sending the thin ACK directly through the address 2, we just hold on and we forward the SYN and the MP join with the token through host B. Once we receive the thin ACK with the MP join from the host B, we just wait again. Then we hold the ACK from the PEP to the host B. Then we send the thin ACK and the MP join we have received from host B through address A. And then once we receive the MP join from address A, we can forward that to host B, and we have Mptcp connection established, even though we have a TCP proxy. So that was the first step. The second step was stranger. Is basically our TCP proxy acknowledges everything at Mptcp level. So the problem that we had is that we realized that if in some experiments we had a loss on the first path, so what happened is in this case, for example, we lose packet 2, and with our open source experiment, we just had the PEPs that was acknowledging the packet 5. I asking for the 5th packet, and because host A receives this acknowledgement, packet 2 is removed for the send buffer. So even though we can adapt our proxy to actually make enable an Mptcp connection despite the presence of the proxy, there are much further modifications required through the open source PEP, so that we can actually have an Mptcp connection that works, because this ends up in connection closing, and we have that just doesn't work. Also, there is something in the that's something that we have also seen If basically on the RFC for MPTCP, it mentioned that we need to have at MPTCP level one unique receive buffer. And the problem is we have here one receive buffer at the proxy level and one receive buffer at the host B level. So we have sometimes encounter also flow control issues. So we were not happy with the results, but we don't like to have proxies. We usually need them. And so we also made an experiment without specific accelerations. So we just have this PEPSAL, which is an open source TCP proxy. We have just used an MPTCP version under the stack, and we have a huge asymmetry because we have 600 milliseconds on the satellite link with download and upload characteristics that are close to what we have in public accesses for internet access with satellite. And on the terrestrial link, we have an RTT that is 120 and 8 meg upload and download. So we have done some downloads. You can see at the bottom left. So that is the downloading time as a function of the file size. And for MPTCP using both links, MPTCP using only the LTE link or the emulated somehow terrestrial link and the satellite link. The good thing is, even if we can't accelerate these MPTCP, if we just let it go through satellite networks without acceleration, we have gains. Despite the very large asymmetry, we are just using the basic and minimum RTT scheduler. So that is a good thing for Earth. We are happy to have this kind of results because we see lots of trends in using MPTCP to do aggregation between different networks. That was the first part of my presentation. The second part of my presentation is speaking about using MPTCP to do link aggregation. In some cases, there's a huge trend in low Earth orbit satellite constellations. You may have heard of the SpaceX one or OneWeb or Telesat one. Well, there are many around. And so sometimes there is interest in doing layer 2 hybridation, but we were thinking that maybe doing that at the MPTCP level would make things life easier at the physical and link layers. So we have done some measurements to see how MPTCP behaves in these use cases. We also have experiments on how they behave if we want to use MPTCP for handovers, but I will present the case where we have basically a client that is behind a box with MPTCP. We have two different satellites available, and we have the MPTCP box on the other side and a server on the other side. We have a variable delay, one-way delay that is close to, basically if the delay is moving, it's because the satellite is going closer and going further away. And we neglect the impact of handovers. Basically, we consider that we always have one satellite that is going closer to us and one that is going away. And so that is a simple model but it's still somehow close to one of the constellation models. So even though with Iridium today you have only a couple of kilobits per second accesses, with these huge mega constellations, we expect to have more decent capacity. What we have done is comparing MPTCP that is able to have 8 megabits on both links. We compare that with a single path TCP using only 8 meg link, but also to have a fair comparison, we compare that with a single TCP that actually have the double capacity, because otherwise we often see in MPTCP comparisons unfair comparisons because we see better performance, but that also just because we have more capacity. So we wanted to have this case as well to see to what extent MPTCP can be as good or not as the single pass one with a double capacity. So this is one of the results we have. So in this case, I have two experiments on that. This one, we have a simple Apache server. So we are not sure that this is, again, the file transfer depending on the file size. And we are not sure that we have reached the maximum capacity that the protocol could have, because we have a limited file size. But what we can see is when we look at the larger file of 100 meg, so TCP with only 8 megabits has 7 megabits per second of good put, Mptcp 11, and TCP with 16 megabits per second, 14. Basically, we see that Mptcp does not do as good as the TCP that has more capacity, but we know that with ODIA and all these mechanisms for fairness, that's also one of the objective of Mptcp, not to grab the whole available capacity. So we are not saying Mptcp is doing bad, but we're also saying that this is what it has been designed to do, and not to grab the whole capacity. But still, we think there might be improvements here in this use case. Also, we thought that we know that there may be some issues on TCP, native TCP, on when you have this kind of variable delay, and that is something we are investigating at the moment. And another set of experiments, because we know that the web is strange. We have this emulated platform. Then we go out on the internet and download real web pages using HTTP2 over TCP. We don't have quick here. And basically we have the same characteristics of Mptcp, single pass TCP, or single pass TCP with a double capacity. So when we look at the first results, we have three somehow simple pages with either HTTP2 or HTTP 1.1. and few redirections. So other domains refers to the amount of redirections that are done on the page. And what we can see is that in this case, if we compare these three web pages, Mptcp in purple does as good as TCP with a very huge capacity, like 15 megabytes. However, when we moved to more complex pages, when we have lots of redirections. So that's the part where I don't exactly understand what's going on, because we see that, for example, for the page Le Monde, even though we have few redirections, we don't see much differences between the time needed to download the page. However, for the pages that are very complicated, we thought that Mptcp was not doing as good as TCP with 16 megabytes. We think that may be because Mptcp opens then lots of subflows, and that may not be as interesting as having one less flow. We don't know if it's a client limits or if it's Mptcp that opens too many things. That's still something that we are investigating. But anyway, we see that as an easy way to handle handovers and to aggregate capacity in the Leo constellation use case. So to sum up, TCP proxies block Mptcp traffic, and we tried that quickly, and adapting TCP proxy is not that simple. And we haven't opened all the Pandora box we may encounter when we want to do that. So we're happy not using TCP proxies if the performance are good, and they are actually quite good. And also we realized that it was very complicated to make a fair comparison with the diversity of the web pages we've seen. And for those who are interested in SATCOM, we have a workshop on Quick for SATCOM tomorrow afternoon.
Thank you. Any question?
Markus Arment, short question. I think it was on slide 10 where you did a comparison between multipass TCP and TCP/S. Did you also play it a little bit with the buffer? Did you also play it a little bit with the buffers? Did you play it with the, did you change the buffers and then try it out if this make a difference?
The buffer at MPTCP level?
TCP buffer, send and receive buffer.
No, that was, we have just done default MPTCP. That was in the kernel. I don't remember which version, but
Yeah, because we have sometimes good experience to adapt a little bit send and receive buffers to get the data rates tuned.
okay. Thank you.
Okay. Hello, this is Yoshi from Fluor. This is my personal curiosity. Yeah, thanks for interesting presentation. So I have several questions. First, I would like to know which kind of implementation you have used. For sender and receiver, did you use Linux implementation?
What implementation we used for?
Yeah, for experiment.
For the PEP, we are using PEPSAL, and for that is written here. That's PEPSAL. That's an open source PEP.
Okay.
And for the stack, we have not been using the same for the two experiments because there are two. One, I don't have the number in my head for the.
That means open source PEP support multipass TCP.
Basically, it depends on the stack on which it is using. So it uses the stack on which it is used. So basically, if you are on a stack with MPTCP version X, PEPSAL is using MPTCP version X.
Okay.
It depends on the Linux kernel it is on top of which it is.
Okay, but when I look at the page 6, I'm not page 6. 5. Okay, that one. I'm not sure if the why PEP sending ARC5 here. I'm wondering if there might be a bug in a PEP implementation. That's why I'm asking what kind of implementation you are using.
Okay, you think that?
Yeah, so that's what I want to know. And then, so other stuff is, can you share the TCP dump file for your experiment? That way, some people have some knowledge about MPTCP can debug the traffic, and then people might be able to identify, okay, this is the reason. I mean, it could be a bug, or it could be some problem of MPTCP.
Okay, you sure? I can share all I can share. I will share all I can on the list. But also, I wanted to, we thought that was the first problems we were encountering. We were seeing more and more problems. So we were like, maybe we don't need any acceleration for that use case. Because of the receive buffer, we had flow control issues, and we're like, oh, maybe we just don't need proxies in this use case. But I can share the problems if that's interesting for anyone.
That would be, I think, useful. Thank you. Okay, any more comments, questions? Okay, thank you, Nicholas. Now, Chi. Now you can use rest of your time. Trust first. Trust is first. Predict. Sorry. It's big. It's coming. It's coming. Okay.
Okay, thanks for chair and thanks for your coming. Hello, everyone. My name is Chi from Tsinghua University, and it's my first time to attend IETF. So please excuse me for anything wrong. Okay. Okay. So as the network changes and develops, we see more and more information, different informations that we could adopt, obtain, and utilize in transportation layer to improve some performance like throughput or security and other things. So today we are bringing two simple and powerful things we want to introduce them to Mptcp and to improve something. So now let's start. The first one is to introduce prediction. And we have submitted the draft, the predictable multipath TCP extension. So what's the predictability we say here? In the emergent networks, we see more and more predictable nodes are involved. So by predictable, we mean they are different from the previous nodes, as they have inherent and thus predictable location information, some of which are at the fixed locations, some specific locations like the ground stations, and others are keep moving. They are continually moving at the expected speed on some predefined orbits or predefined routings on Earth, on the ocean, or in the space. So like the low Earth orbit satellites, the geostationary satellites, and the air aviation crafts, and the ships, and so on, they have predefined routings, and we can predict their locations. And furthermore, because the relative position between them can be predicted, the state of the network NICs can also be predicted. So to be specific, the predictable information are include, but not are limited to this. For like some link handover, like if you have an aircraft that's connecting to the internet with the air to ground broadband, that's the connecting to the stations, the base stations on the ground, and the aircraft is keep moving. The link will hand over. So we can predict the time the handover happens, the link bandwidth and delay before and after the handover happens. And for some on-off switch, and that is if some link is will continually disconnect and reconnect, disconnect and reconnect, we can predict the time the disconnection and the reconnection happens, and the link bandwidth, the RTT, when the reconnection happens. So how can we utilize them? Here is an example to show a scheduler using prediction information. As we can see in this scenario, aviation crafts are connecting to the internet with Mptcp, and it's simultaneously using air-to-ground broadband and satellite communications. And what's more, because of the complicated topography, like some mountains or rivers, the base stations on the ground don't appear at anywhere on the ground, so it leads to the discontinuity of ATG broadband. That means the ATG broadband link may be intermittent and therefore defeats the quality of the whole Mptcp performance. So we want to introduce the prediction informations, and we have a modified version of the Mptcp called Mptcp. The default scheduling principle of Mptcp is minimum RTT principle, and we introduce these two prediction information, that the time the next disconnection happens and the time the next reconnection happens, and they are denoted as the time down and time up. So it's very simple modification. The original RTT was calculated by the default method is called the RTT original. Of course, we reserve it. And when the ATG link is connected, the RTTP equals to RTT original. However, when the link is disconnected, it's calculated as RTTP equals RTT original plus RTT time up and minus time now. And actually, the RTTP will denote the actual time that if you send a packet now, the RTT of the packet. So the Mptcp schedules the packets in the minimum RTTP principle. So please pay attention. Here is how the enhancement we can get through the modification. The original Mptcp takes time to find a link disconnected or reconnected, and then it will accordingly schedule data and packets to different paths. And with the prediction information introduced, when a link is going to disconnect, the Mptcp could reduce the packets to be allocated to that path. And also, it can take other strategies like canceling the timers for the packets sent on this path because the retransmission will be meaningless. And when the link is going to reconnect, Mptcp can allocate some packets to it at the time once it gets reconnected. So for the next steps, if you may notice that in the example we mentioned, sometimes actually we need to keep the temporarily disconnected subflow valid when it's disconnected for quite a period of time. And it might be necessary to do some more measurements, like to set it to a backup mode, or to inform the other part, the other and the state that is to inform the other end that it will get connected. What's more, some extension to TCP may also be needed, and we are thinking about this, working on this. If you have any suggestions, please tell us. And so what's more, we are here to encourage the whole community to find more ways to use these prediction informations for the emerging predictable network nodes. Like if you find some new modifications that you can make with prediction information, or you think we should build a framework to obtain and to use this prediction information. So please tell us if you have any suggestions or questions.
Hi,
Hi.
my name is Spencer Dawkins, and but please excuse me if I get anything wrong also. Welcome. So I really appreciate you bringing this work here.
Thanks.
The IETF has had efforts in the past to try to say, if I know something about changes to link state for some reason, and a number of years ago, this was, I noticed that I've lost my cellular signal on my cell phone. You know, I know that. So I could tell the TCP on my cell phone, and it could use that information in some way. That hasn't worked in the past, but you're not talking about the same kind of TCP that we were talking about in the past. You know, you're not talking about one path, which is what a lot of the work that I was involved with was doing. So this might be different enough to where this could succeed, where previous attempts in this space have not succeeded. I am in Path-Aware Networking Research Group. I am draft author for a draft. The file name for the draft is What Not to Do, and it describes one of my own failures in this draft. So I would love to talk to you about that and about how this might be different. But I really appreciate you bringing this work here, because if we could do something with multipath TCP, that is a dream that I have had since 1998. Thank you.
Thanks.
Any more comments? Okay, move on to the next one.
Okay, thank you. And to compare with TCP, we believe that Mptcp could simultaneously use different paths, especially the paths of different characteristics. And the next one we will introduce is trust.
Yeah, bar is moving.
Yeah, it is moving. It's coming soon. So trust is crucial in our own human modern society, and we believe it's very important for the internet. And the researchers have been working for many years towards a trusted internet.
Something wrong. Okay. Yeah.
So today, trust in internet has been supported by more and more infrastructure and is being supported by more and more. So the accountability is a very important part of trust. For example, the source address validation, that is SAV mechanisms, are developed to prevent nodes to spoof other nodes' IP addresses and to do something malicious. And thus, all the IP address in the net will be accountable and thus improve the accountability of the internet. Savi and Sava they have their own RFCs. So Multipass here is being faced with some challenges caused by the control packets sent by some malicious hosts with a forged IP address. So we are here to propose to extend Mptcp to work with SAV, and so that it can improve the accountability of the whole Mptcp connection, and also the security can be improved because the IP addresses can be accountable. So here is what we have extended. So here we define an IP address is trusted if it's protected by Savi or Sava. And if on one subflow, the source IP address and the destination IP address are both trusted, we call the subflow a trusted one. And then for the control packets of Mptcp, they will be preferentially sent through the trusted subflows. That means Mptcp might simultaneously utilize different paths, some of which may be protected, that is trusted, and some may be not. So for the control packets that may be used to carry out some security issues, it can be protected if we send all the control packets, the vulnerable control packets through the trusted path. And if there is no trusted path, the Mptcp will just performs as usual. So this is what, and to be specific, the details we have. First, we have extended the original add address option to carry a more flag, that is a trusted address flag passively when you add one address. So, and secondly, to make sure that both parties for an communication path know that the subflow is trusted or not, we have proposed a new option, that is address trust, to notify the trusted address proactively. And third, we will record this trusted informations in one table called trusted path spanning tables to maintain the trusted subflow state, so that when we want to send control packets, we can send it from the trusted one. So here is the trusted address notification. We have extended the add address packet. So we have a T flag, if you notice, the flag T is to indicate the whether the address is trusted, and the flag E as original is to guarantee the reliability. And what's more, the truncated HMAC is a HMAC of address and the trust flag, which can protect that the trust flag is true. And this is how it was interacted. And the second, this is a trusted connection notification. So if one connection has been established and you don't know whether if it is trusted, you can send your own address at the address 1 and send it to the other. If the other is also trusted, it will send it back and to change the flag E into 1, so that you will know the both ends of the subflow is trusted, and you can add one entry into the trusted path banding table. So in this table, every subflow consists of a source address IP and a destination address. If the source address and the destination IP address are also trusted, the subflow is called trusted. And so when you want to send some trusted or the control packets, you can check this table and send it through a trusted flow. Okay, thanks. That's all, and we really need your comments and questions. Thank you.
Questions? Comments? So,
Okay.
yeah, this is interesting. But so I'd like to know about the next step of this one. So are you going to implement this one or making prototype or something? What you are thinking?
Okay, actually for the trusted one, we do have some implementation, and we have a paper that has not been published. And for backup, this is a framework that we have implemented to we call it a trusted Mptcp. And we have 3 new objects, like the trusted address notify, to mark, and the trusted path choose, and add into the original Mptcp architecture. And we have also evaluated it, and it works, and it will, the CPU usage of it is lower than the regular Mptcp. So, do you have any suggestions for our next step? Or
Yeah, if you can do some experiment and then come back with this meeting, that would be, I think it's interesting, and then it can stimulate people to work on this thing. So, and there are some comments.
Hi, Stu Card. Wondered whether you're interested in exploring stronger notions of trust, such as perhaps you might have an IPsec ESP tunnel between a pair of those IP addresses, which would obviously give a higher level of trust than merely a verified address. Does that help in any way, do you think?
I'm sorry, can you repeat your question?
Okay.
Sorry. Wonder if you believe there is any potential benefit to exploring stronger notions of trust than merely a verified address, such as, for instance, an IPsec encapsulating security payload tunnel that might have been built at layer 3 between a pair of those source and destination IP addresses. Obviously, there's additional overhead associated with that, but there's also a greater degree of trust.
So actually, with the development of security or network, the internet serves for the applications. So at last, if the application doesn't know whether the trust, the path or the connection is trusted, it cannot do some selections or according to it. So if we can do more implement more stronger security on the transportation layer. We can tell the application layer whether it's secure or not, so the application can also utilize this one. And is that clear? And maybe another.
Hi, Brian Trammell as JavaScribe from Hong Kong. Do we need to store the TCP ports as well, because CGNAT might actually change the source and destination IP address? Or is this NAT, does this work in a CGNAT environment?
I'm sorry?
The question is like the literal question, do we need to store TCP port also, since CGNAT may change source dest IP address? So I'm interpreting that as, does this work in general in a CGNAT environment?
CGNAT?
Carrier grade NAT. So you basically have like large scale changing of the source destination ports and, the source port and address, and then the destination port and address on the backside.
If you, maybe not.
Maybe not. Okay.
Yeah.
Yeah. Thank you.
Okay.
Yeah. Ho Li from Tsinghua. That one more additional information for our solutions. Yeah.
Cross
we
your
believe,
mic.
yeah.
What? Speak louder, please.
Speak? Okay. 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 Thank you. That for security from application layers, we need some trust information from IP address. If we have a true IP, there is not fork IP. Like some DDoS services can be avoided from CDN services. So this is why application need much information, not only by the IPsec and by other supported from network layer. So this is why we have sub-infrastructures. In the fact, for China, there we have Cernet and Cernet 2. We have established to establish some sub-infrastructures to support it. So we have that. If we know this from application layers, know this IP cannot be forked, so we can do many research and support it on it. This is some remedy information.
I see. But does this framework cannot be used without SABI? Is there a several way to trust the IP address, just like IPsec? Right now, it's presumption of the existence of SABI. That's this framework. So you always presume SABI framework?
No, I think if any framework can tell us the information, we can utilize it.
Okay. Any more questions? Okay, thanks so much.
Okay, thank you.
Thank you. So it's 10 minutes early, but it's okay. And then thanks so much for many interesting presentation. And I cannot say let's meet Vancouver right now, but let's enjoy social event. Thanks so much. Anybody has blue seat? Please bring it to me.